Hi, this is the review video for test number 2. So I'm going to, like the video for the review for test number 1, I'm just going to go over selected or the solutions to selected problems from the review sheet, but I'm not going to cover every problem from the review sheet. Of course, the answers, the complete solutions for the sample test, the review sheet are posted on our class webpage in Blackboard. And this video will remain posted up until the time of the test, and then I'm going to take it down temporarily while you're taking the test, and then I'll restore the link after you've turned in the test, right after the due time for the test. Okay, so let's start looking at some of the problems here, and I'm going to start with the very first problem, which is just a very basic problem from differential calculus. Whoops, I scrolled a little bit too far there, so let me scroll back up. So what this problem does is state a function, a formula for a function here, x cubed minus x squared minus x, and then in a kind of a friendly fashion here, problem also gives you the derivative for this function. You can verify that this is the correct derivative really easily. So there's the derivative function here denoted using the, again, the fashion notation dy over dx, and it's 3x squared minus 2x minus 1. Here's the graph of the original function. This is not the graph of the derivative function, but this is the graph of the original function. And so we're just asked to use that derivative to answer a couple of questions, I think, about the original function. First thing, though, we're asked to do, though, is just evaluate the derivative, right? Evaluate the derivative at x equals 0. So again, this is we're using the old-fashioned notation to indicate evaluating the derivative at a particular input. So this is the notation for evaluating the derivative at x equals 0, right? So we draw this vertical bar and then write the x equals 0 here as a subscript. And all that means is we just want to plug 0 in for x, right, in the derivative. So that's an easy calculation to do, right? Just plug 0 in for x. And when you do that, these first two terms will disappear because you're multiplying by 0 in both of these terms. When you substitute 0 for x, and then you just end up with minus 1. So so the value of the derivative at 0, right there on the graph, the value of the derivative is minus 1. That looks kind of like it's plausible, right? Because indeed the curve is decreasing here at 0, right? And it looks like it could have a slope of minus 1, but that's what the derivative is telling us, right? The slope there at 0 is minus 1. And then we want to use the derivative to answer this question. So a very typical question in calculus, right? We want to find in this case, the negative value for x where the tangent line is horizontal. Okay, so we want to use the derivative to answer that question. If you look at the graph, right, you can see that over here on the left-hand side, right, to the left of the y-axis, there is right there, it looks like, right, a place where the tangent line is going to be horizontal, right? Right about here, it looks like the tangent line is horizontal. Of course, that corresponds to a relative, in this case, a relative maximum, right? A turning point on the graph. Okay, in this case, it's a peak turning point. But we wanted to, we can't estimate very clearly from the graph what that x value is, right? So we want to use the derivative to find that x value exactly. There's another x value over here on the right-hand side, right there. It looks like at x equals, is that, I can't read the graph very well. Is that x equals 1? I think so. Where there is another place where the tangent line is horizontal, correct? But we want the negative x value. So we want to find this value over here on the left-hand side. But we can find both of those values from the derivative, right? Because horizontal tangent line is going to have slope 0. And remember, the derivative is what we use to find the slopes of tangent lines, right? So we would simply take that derivative that we were given, 3x squared minus 2x minus 1, and set it equal to 0. So this is a very common process in calculus, taking the derivative and setting it to 0. And exactly the purpose of that is to find where tangent lines are horizontal, or where we have peak or valley turning points on the graph of a function. So we're left with solving this equation, 3x squared minus 2x minus 1 equals 0. Now, that's a quadratic equation, so we have lots of options for solving that equation. We could use the quadratic formula if we needed to, but here we can solve by factoring, because this trinomial, 3x squared minus 2x minus 1, that is going to factor. So it factors, in fact, as a 3x plus 1 times x minus 1. And so that means that either 3x plus 1 must be 0, or x minus 1 has to be 0. And then you just solve these two simple equations to find x, right? So you come up with x equal minus 1/3, or x equals 1. So here is the negative x value, right, that makes the derivative 0. Or here's the negative x value where the slope of the tangent, where the tangent line is horizontal, where the tangent line has slope 0. So minus 1/3 is what we were looking for in that case, right? So be prepared for this sort of question on the test for sure, right? Because this is a very common sort of question in calculus. All right, now the second question is also a differentiation question, but it's harder because this one involves implicit differentiation. So here we no longer have a function, we just have the graph of a curve. So here's the equation for that curve, x squared minus x y plus 2y squared equal 8. It turns out when you graph this equation, you get this nice ellipse that has been slightly rotated, right? Okay, it's been tilted a little bit, and but it is an ellipse, okay? And so that's what that's the curve that this equation yields when you graph it, okay? And remember, we can use implicit differentiation, right, to answer calculus sorts of questions about curves that are not functions, right? And so that's exactly what we're going to do in this. That's exactly what we're going to do in this particular problem. So here we have already got an expression derived for the derivative dy over dx. And so we're just told, oh, dy over dx is can be computed from this formula, y minus 2x over x plus 2y. Okay, so normally you would find that formula, right, for the derivative by using implicit differentiation, which we've been practicing, here recently, right? But in this case, it's already done for us. All right, so there is the implicit derivative, right? And so now we can use that implicit derivative to, find the slope of this curve at particular points on the curve, right? So in fact, that's what we're asked to do here. Immediately, we want to evaluate the derivative when x is 2 and when y is 2, right? Notice in this formula, you need to have not only a value for x, but you need to have a value for y as well. So that's why when we're asked to evaluate the derivative, we're given a value for x and a value for y. So so we just plug that into our implicit derivative formula, right? And 2 in for y and 2 in for x, and do the arithmetic, and you come up with minus 1/3, right? So what that tells us is, maybe that's the next question here, but what that's going to tell us is at the point a 2 on the graph, x equal 2, y equal 2. So right there at this point, apparently that point is on the graph, x equal 2, y equal 2 is on the graph of this ellipse. We know at that point, the slope of that curve is minus 1/3. In other words, the tangent line is going to have slope minus 1/3. That looks like it's kind of plausible, right? If you think of drawing a tangent line to this curve, right at this point, 2, 2, that tangent line is going to have negative slope. You could see that tangent line is going to be going downhill from left to right. And in fact, the tangent line is going to have slope minus 1/3 according to this derivative, right? And so, oh, that is the next question. Oh, no, well, almost the next question, right? It says in part B here, write the equation for the tangent line to the curve at the point, this point here, 2, comma 2. Well, we know the slope of the tangent line is going to be minus 1/3. That's what we just calculated in the prior problem. And now we just use our slope, our point slope form, right, to write down the equation for the tangent line. So you write y equals, right, the slope, right, times x minus 2, because that's the x coordinate of the point, and then plus the y coordinate of the point that you're given, which is also 2. So there's the equation for the tangent line. Now, in the next problem, we're going to sort of repeat all of this process, except we have to do the implicit differentiation. Okay, so here we have another curve, which is not a function. Never mind the straight line here. We're going to talk about that in just a moment. That's a tangent line. But the curve that we're interested in here is this a loop curve here. This is called the Folium of Descartes. So it was Descartes, the French mathematician, who apparently studied this sort of curve first. Descartes predates calculus, so Descartes lived, or calculus was invented. So when Descartes studied this curve, he did it without using tools from calculus. All right, so first thing we want to do here is find the implicit derivative that we can use to find the slope of this curve at different points. So we're going to go through the implicit differentiation process here, right? So that's what we're practicing with. So remember, to do implicit differentiation, you're going to differentiate all the terms in the equation, left and right. It's very easy to differentiate 0, though, so I'm going to start with that one, because 0 is a constant, and derivatives of constants are always 0. So the derivative of 0 is 0 itself. So when you do the implicit differentiation here on the right-hand side, you're going to get 0. So that's easy enough. The left-hand side, of course, is going to be harder. So let's differentiate the left-hand side. And again, we have to go term by term to carry out the differentiation, right? So we'll start with the x cubed. And remember, we're taking the derivative with respect to x. So we're thinking of x as being the input variable and y as being the output variable. So we're thinking of y as being a function of x for the purpose of this problem. Well, when you differentiate x cubed, since you're differentiating with respect to x, this is just differentiating x cubed. There's nothing unusual about differentiating this term. So when you differentiate x cubed, you just use the power rule, right? So you bring the 3 down and subtract 1 from the exponent. So you get the derivative of x cubed is 3x squared, just as like you would expect it to be, okay? Right, so that's easy. It's the next 2 terms that are going to be a little bit trickier. And when you differentiate y cubed, because you're differentiating with respect to x, you're thinking of y as being a function of x, the chain rule is going to get involved here. And so you just sort of have to remember that when you're differentiating y using implicit differentiation, that's a little bit more complicated, right? Okay, so you can still use the power rule. You can bring down the 3 and subtract 1 from the exponent. So you do get 3y squared when you differentiate this term, just like you would expect. But because we're differentiating with respect to y, we have to multiply in the derivative of y with respect to x, which we don't quite know, right? Okay, we don't know what dy dx is. That's kind of the whole point of this problem, is to discover what dy dx is. So since we don't know it exactly at this point, we will just write down, I need to multiply in the derivative of y. So you can call that dy dx, or you can call that y prime. All right, so this is the derivative of y with respect to x. We don't quite know what that is yet, so we're just going to have to denote it symbolically, right? Okay, and we'll figure out what it is later. This is the chain rule in action, right? Okay, so bring down the 3, subtract 1 from the exponent, so you get 3y squared, and then multiply in the derivative of y with respect to x. Okay, so there is the derivative of the second term. Now, the third term also has its complications in it, because this is a product, okay? So notice this term is formed by multiplying 2 things together, 2x and then y, okay? So I'm going to have to differentiate this using the product rule, okay? But the product rule is pretty easy to use, right? So so let's do that. So so I'm thinking of 2x as being the first factor in my product and y as being the second factor in my product. So what does the product rule say we're going to do to differentiate this product? Well, it says first, take the derivative of 2x and multiply it by y. Keep the y and multiply by the derivative of 2x. So that gives you 2, because the derivative of 2x is 2 times y, okay? All right, that's the first part of the product rule. Now, what's the second thing? Second thing is keep the 2x, right? Okay, and then multiply by the derivative of y. So I keep the 2x, right? Okay, and then multiply by the derivative of y. But what's the derivative of y? Again, I don't know that exactly. That's what I'm trying to find, but I have to write something in here for the derivative of y. So we'll just write y prime, right? My sort of symbolic name for the derivative of y. Okay, and then we'll worry later about how to figure out what that actual derivative of y is, right? So there is altogether here in the parentheses, that is the derivative using the product rule of this term, this last term, 2xy. Now, be careful about the sign. So that's a tricky thing in this problem. This is minus this product. So in your differentiation here, in your implicit derivative here, be sure to put minus, and then, because this minus and this minus are the same, and then put in parentheses the derivative you got, which was 2y plus 2xy prime. Okay, so group this derivative of this term behind a minus sign to match this minus sign here in the original equation. Now I think I just multiplied through the minus sign here to get rid of these parentheses, and there it is. So there's an equation, 3x squared plus 3y squared y prime minus 2y minus 2x y prime. And that actually answers this part, because all we were told here is differentiate both sides of this equation with respect to x. Okay, now, of course, immediately what we're going to do with this equation that we've got is we want to solve it for y prime. When we solve it for y prime, then we will have a formula for the derivative y prime, right? Okay, so we don't know what y prime is yet, but when we solve this equation for y prime, then we will have a formula for that derivative y prime, and then we can use that formula to answer questions about this curve, this Folium of Descartes. So how do I solve this equation for y prime? Well, we practiced that now several times in class, right? So remember, you're going to, let me go back. Remember, you're going to separate terms, right? So you are going to keep the y prime terms, the terms that have y prime in them. That's these two terms, right? I'm going to keep them on one side of the equation. So I'm going to leave them on the left-hand side of the equation. So these two terms that involve y prime, I'm going to leave them on the left-hand side of the equation. And then the other two terms that don't involve y prime, I'm going to move them to the other side of the equation. So I'm going to pull this term and this term back over to the right-hand side of the equation. And when I do that, I have to change their signs, right? So that's what I've done in this line. I moved these two terms that were on the left-hand side of the equation originally. I pulled them back over to the right-hand side of the equation. When I did that, I changed their sign. Now, I'm got to finish solving this equation for y prime. So what I'm going to do now is, since all these terms on the left-hand side, by design, all these terms on the left-hand side have a y prime in them, I'm going to factor that out of these two terms. So that leaves me y prime times 3y squared minus 2x, right, equals, and then, you know, the 2y minus 3x squared that we had on the originally on the right-hand side, okay? And now to finish solving this equation for y prime, just divide both sides by 3y squared minus 2x. So divide both sides by 3y squared minus 2x, and that get this. So there it is. There is your expression. There's your formula for the derivative y prime. It's 2y minus 3x squared over 3y squared minus 2x. So to evaluate this derivative, we need a value for both x and y. Well, that's exactly what we're going to be given in the next problem. So in part C, it says, use your answer from part B to find the slope of the tangent line to that curve, that Folium of Descartes at the point 1, 1. So that's easy to do now, right? Because you have this formula for the derivative. So you just plug in 1 for y and 1 for x into this quotient and simplify the arithmetic, and you end up getting minus 1. So at the point 1, 1 on that Folium of Descartes, the slope of its tangent line is minus 1. If you take a look now at the graph, there I have it. This is the tangent line at the point 1, 1. Here's the point 1, 1. And so I've drawn in the tangent line at that point. And notice that tangent line has slope -1, just as we knew it must, right, from this problem. Now, let's sort of do this this same kind of applications of derivative, but now let's put them in an applied context so you can see how derivatives would be useful in this case in an economics setting. Okay, so so in this problem, we're given what's called a profit function for the sale of this item, Benny's beach sandals. Okay, so this function you can use to determine what the profit is going to be from the sale of Benny's sandals when you have a particular, this is daily profit, when you have a particular daily demand of X sandals. In this case, the X, though, is going to be measured in hundreds of pairs of sandals. All right. So if you sell X hundred pairs of sandals, then you can use this function to determine what the profit, not the revenue, but the profit is going to be in hundreds of dollars from the sale of those sandals. So this is called a profit function, and these are quite common in business and economics. Okay. All right, so the first question is not really a calculus question. This is more of an algebra question, really more of a arithmetic question. It says, evaluate P of 6.25 and then interpret this value. Well, we've been doing this sort of problem, right, from day one, correct? So we just calculate P of 6.25, right, and then we just plug 6.25 in for X in our profit function and go through the arithmetic, and you get 28.125, right? So what is that telling us? That tells us when our daily demand is 6.2500 pairs, so that's 625 pairs, right? Remember, our demand is measured in hundreds. Then the daily profit is going to be $28.125 because we're measuring our profit in hundreds of dollars. Well, $28.125 is $2,812.50. Okay, just take this and multiply by 100, get $2,812.50. So when the daily demand is 625 pairs of Benny sandals, when we sell that many sandals in a day, or when Benny sells that many sandals in a day, then Benny will make a profit for that day of $28.12.50. Okay. All right, now this next question also is not a calculus question, but it is an interesting question. But not a calculus question. This is more of an algebra question. So the question is, what's the break-even point for Benny sandals? Break-even point means how many sandals does Benny have to sell in a day so that he breaks even, right? Breaks even means he doesn't lose money. He's not going to make a profit, right? But he's not going to lose money either. Okay, so when you break even, that means your profit is zero. It's not negative and it's not positive, right? Okay, and so to answer this question, you simply take the formula for the profit function and set it to zero. Set your profit function to a profit of zero, and then solve this equation. Okay, and that will give you the two x-intercepts of the profit function, right? the two x-intercepts of the profit function are going to be the break-even points for Benny, right? That's the his sales amount, so that he breaks even, doesn't make any money, but doesn't lose any money. So you just have to solve this equation, okay? And so that takes a little bit of effort. It's a quadratic equation, but not much effort, because you can actually solve this by factoring. So I showed the steps here to solve this equation by factoring. So I'm not going to go through those. You can follow those steps easily. And it turns out your two break-even points, the two solutions to this equation are x = 5 halves and x = 10. So if Benny sells 250 pairs, he will break even. If Benny sells 1,000 pairs, he will also break even. You may wonder, why are there two break-even points? If Benny breaks even by selling 250 pairs, why doesn't he have even more profit when he sells 1,000 pairs? So why is his profit, gotten to why has he gotten to break even at 250 pairs, but then he's also break even at a larger amount of sales, right? Why has he gone back to break even? And the answer to that question has to do with price and demand, right? Okay, so so probably what has happened here, in order for Benny to increase the demand to 1,000 pairs, Benny will have to lower his price. But when Benny lowers his price, of course, that's going to impact his profit, correct? So that's why there's two break-even points, okay, and not just one break-even here. Okay, so now let's get to the actual calculus, though, right? Okay, all right. So this is the only problem on the review where you actually have to apply the limit definition to the limit process to find a derivative function. All right. So, but you can be certain that such a question will be on the test. All right. So you will need to be able to go through the steps of this limit process to find a derivative function. Of course, we've got all our great shortcut rules for finding derivative functions. So this limit process is kind of primitive. This is what we used when we were first learning what derivatives were, right? But you will need to do this at least once on the test, okay? All right, so remember, to find the derivative to find the derivative, right, for the profit function, then here is the expression that we need to evaluate, right? Okay, you're going to take the limit as h approaches 0 of p of x plus h, right? P of x plus an increment minus p of x, and then over x plus h minus x. Remember, that denominator is going to simplify to just h. So so you have to compute p of x plus h. That's what I've started here with, right? I plug x plus h in for x into the profit function. So you get 25 times x plus h minus 2 times x plus h squared minus 50. That's just the profit function evaluated at x plus h, minus then just p of x itself. Well, p of x is just that formula, right? 25x minus 2x squared minus 50. Notice I've grouped this p of x in parentheses behind the minus sign, right? So be careful that you do that so you don't make a sign mistake. This minus sign is the same as this minus sign. And p of x, since that has 3 terms in it, I have to put those 3 terms in parentheses. 25x minus 2x squared minus 50. And now, remember, and then you're going to eventually here, we're going to compute the limit of this expression, right? This quotient as h approaches 0. But we're a long ways from doing that yet, right? So next, we're just going to do a bunch of simplification, right? You're going to go ahead and do the algebra here, multiply 25 times x plus h. You square the x plus h and multiply it by 2. So that's what I'm doing here, right? Remove the parentheses from around these 3 terms, right? Just distribute the parentheses, right, to remove the, distribute the minus sign, right, to remove these parentheses, right? So here I'm just grinding through algebra in order to simplify my numerator. Okay, so I did a little simplification here, then a little bit more simplification, then added a bunch of like terms, a bunch of terms cancel, and eventually you get down to the limit as h approaches 0 of 25h minus 4hx minus 2h squared all over h. And then that simplifies nicely because h in the denominator who will divide into all of the terms in the numerator. So h goes into 25h, that leaves you 25. H goes into 4hx, that leaves you minus 4x. And then h goes into the minus 2h squared and leaves you minus 2h, right? So you can reduce this fraction. You can cancel the denominator here in this fraction, right? By dividing it into all three of your terms in your numerator. So you get the limit as h approaches 0 of 25 minus 4x minus 2h. And it's easy to see that's going to be 25 minus 4x, right? Because as h approaches 0, this term minus 2 times h will also approach 0. So this ends up being infinitesimally small as h approaches 0. So ultimately, you're left with just 25 minus 4x. And so that's how we get that our derivative of our profit function is 25 minus 4x. So that's easy to find using our differentiation rules, but here we went through the full limit process, right, to find this this derivative. All right, now let's see what we can do with that derivative. Now we've got that derivative, but what can we do with it? So in part D, it says, use the rate of change function to find the x value where the tangent line is horizontal. Okay, so now we know how to do that easily, right? We just take our derivative and set it equal to 0 and solve that equation. So you end up getting x is 6.25. So it's at x equals 6.25. That's where the tangent line to this profit function is going to be horizontal, and that leads us to believe, right, that that we're going to have a maximum profit at 6.25, right? Because where the tangent line is horizontal, that means either you have usually you have a peak turning point, right, or a valley turning point where the tangent line is horizontal. In this case, it must be a peak turning point, right? So it must be our maximum profit, or our profit is going to be maximum at x equal 6.25. And when you plug 6.25 into the function, the profit function, you get 28, 12, 50. Okay, so it looks like that we have a maximum profit of $2,812.50, and that occurs at when our sales are 6.25 or 625 pairs. Okay. All right. Let's look at one more here that I'm going to take. I'm going to pause the recording for a minute, and then I'll come back. So in number 5, this should be pretty easy. Here we're given the graph of not a function itself, but a derivative of a function. Okay, so we're thinking about a function called f, and we're not given the graph of f, so we don't know what the graph of the function f looks like exactly, but we are given the graph of its derivative. So here is f prime of x, all right? So that's a little bit unusual, right? Dealing with a function, and just know it's, all we know is its derivative function, okay? And now here's the question. Find all the values on the graph of f, the original function, not the derivative, okay? But where on the graph of the original function do we have a horizontal tangent line, okay? Wow, how are we going to answer that? We can't see the graph of the original function. All we have is the graph of the derivative function. So how do we know where the original function f has a horizontal tangent line if we can't see its graph? Well, remember, this is what calculus is all about, right? This function is going to have a horizontal tangent line where the derivative is 0, right? Okay, where f prime of x is 0. Now, we don't have the formula for f prime of x, so we cannot solve this equation to find x, but we have the next best thing, right? We have the graph of the derivative, and we can see that the derivative is going to be 0. Where's the derivative going to be 0? Right here at -2, right? See, at x equal -2, notice the derivative there is 0, right? Because that is an x-intercept. And then also here at 2, we can see that f prime of x is going to be 0, right? The matching y value for the input 2 is 0. The matching y value for the input -2 is 0. So f prime of x is 0 at these two x-intercepts, -2 and 2. So really, just having the graph of f there makes it very easy to answer. This question. So didn't have to do any algebra there, right? Okay, we can answer the question there just from using the graph. All right, so let me pause the recording here, and then I'll come back and we're going to continue more problems from our review. Okay, so let's resume here by looking at problem number 6. This one you have to look carefully at, okay? Because there's 3 graphs drawn on the same set of axes, so it kind of looks a little bit like spaghetti. So we've got an original function, and then f, okay? And then we have a function, its derivative, f prime, is graphed, and then we have the second derivative, f double prime, is also graphed. And we're asked to figure out which graph is which, okay? So in the original problem, I don't have any of these graphs labeled, right? And so you're the one that has to figure out which of these is f, which is f prime, and which is f double prime, okay? And then sort of explain the reasoning, why you chose, which curve is being which graph. The clues here that you can use are kind of related to the previous problem number 5. All right. So what I want you to know here, what I want you to notice here is look at this. Look at the solid graph here. Okay. This appears to be a parabola. This graph, and notice that. Look at its x-intercept. So it has an x-intercept there at about kind of close to 2, and then another x-intercept here right about there, which looks like that might be about -1/4. The exact value is not really important, okay? But what is important to notice is that the intercepts for this, the solid graph, notice they match up exactly with the turning points for this function, okay? The dashed function. And that's really an important clue, right? Okay, because remember, the peak or valley turning points on a function, you can find those by finding where the derivative is 0. So if you were looking for the peak or valley turning points on this dashed curve, right, you would do that by looking for where the derivative is 0. In other words, the x-intercepts of the derivative. But that happened. But the peak or valley turning points for this dashed curve, they happen to occur exactly where you have x-intercepts for the solid curve. So that's a strong clue that that the dashed curve is our original function f, and the solid curve is its derivative, because the x-intercepts of this solid curve match up with the peak or valley turning points, right, of the dashed curve. So that's how I deduced that this dashed curve was the original function f, and then the solid curve is its derivative f prime. Now, how do I know that this is, how do I know that this, the dotted curve here is f double prime? Well, so remember, f double prime is the derivative of f prime, right? Okay, the second derivative is the derivative of the first derivative. So, so the first derivative has a valley turning point right about here, correct? Right, okay. And notice that matches up perfectly with the x-intercept for the dotted curve. So see, that's a strong clue that the dotted curve is the derivative of the solid curve, right? Because again, the x-intercept of the dotted curve matches up with the turning point of the solid curve. So that's how I decided, oh, the dotted curve is the derivative of the solid curve, right? Well, the solid curve is already the first derivative, so that means the dotted curve must be the second derivative, okay? So that's the sort of reasoning that you can go through to figure out which of these curves is which. Now, the second part here also says, well, what's going to be the formula for the third derivative, right? Okay. Well, the third derivative is the derivative of the second derivative, correct? So we already decided that this dotted curve is the second derivative. So we're looking for what is the derivative, the third derivative, right, of this, what is the derivative of the second derivative, okay? So what's the derivative of this dotted curve, since this dotted curve we think is the second derivative? Well, we don't have a formula for f double prime, unfortunately, so we can't just write down what its derivative is, right? But we get a little bit of a break here because this dotted curve is a straight line. And because it's a straight line, we know its derivative is its slope. So remember, the derivative of straight lines is just the slope of a line. So if we can just calculate the slope of this dotted line, then we know what the third derivative is going to be, right? Okay, well, we know what the derivative of the second derivative is going to be, but the derivative of the second derivative is the third derivative. So so all we have to do is figure out what the slope of this dotted line is. So that's pretty easy to do. You just have to pick off a couple of points, find a couple of points that you think are on this dotted line. So these are 2 points that I thought were on the dotted line, and then I just calculated the slope between those 2 points, and it turns out to be 16. So I think that the derivative of the second derivative, which is better known as the third derivative, is just the slope here, 16. Okay. All right. So one thing to keep in mind, this came up several times in the homework, is remember straight lines, their derivatives are just their slope. Okay. So if you have a straight line and you want to know what its derivative is, it's easy. Just find the slope of that straight line. Okay. Let's see one more sort of graphical question, I think, and then we'll move on. To some different sorts of things. So this question number 7 is, we had a homework problem similar to this one. So suppose we've got a function named p, and it happens to be the product of these two functions f and g. Unfortunately, I don't have the formulas for f and g. If I had the formulas for f and g, I would just multiply those two formulas together, and then we would have the formula for p, correct? But we don't have the formulas for f and g. All we have are their graphs. But just using, so we don't know what their formulas are, but just using that information, we want to figure out what is the rate of change, what is the derivative of p at 2. So that seems like a really unfair question, right? How do I figure out what p prime of 2 is? I don't even have a formula or a graph for p, right? Okay, So how can I figure out what p prime of 2 is? I don't really have much to go on, but we do have a little bit to go on because we know that p is the product of these two functions f and g. So what that means is if you want to compute p prime of 2, if you want to compute p prime of 2, you can do that using the product rule, right? You can do that using the product rule because p is the product of these two functions. So the product rule would say what? You would take the derivative of the first one times the second one plus the first one times the derivative of the second. That's exactly what I've done here in this equation, right? I took f prime of 2 because I wanted to know what the derivative of p was at 2, right? So I took the derivative of f at 2 times g of 2, right? F prime times g plus, and then kept f of 2, so kept f, and then multiplied by g prime of 2. So you see, this is just the product rule, except instead of using the variable x in the product rule, I used the input 2 because that's what I wanted to find. I wanted to find what was p prime, not what was p prime of x in general, but what is p prime of 2. All right, now, well, that gives us a place to start. Let's see what we can fill in here, right? So, well, we got to figure out what is f prime of 2. So we have to think about that. Okay, but g of 2 is easy to calculate. Just look at the graph of g. See, here's the graph of g, right? There's 2. And so there it is. You can see that g of 2 is going to be 5. So very easy to fill that in. And f of 2 is also easy to calculate. There's 2, and there's the graph of f. So that looks like it's what, 3? Right, okay, so just look at the graph and you can find that f of 2 is going to be 3, and then we have to multiply that by g prime of 2. Now the question is, what is f prime of 2 and what is g prime of 2? How can I find that just from looking at the graphs of f and g? Well, here we go back to this same piece of information that we were using in the previous problem, right? The function f is a straight line and the function g is a straight line. So their derivatives are just their slopes. So if you can find the slope of f, you will know what f prime of 2 is. And if you can find the slope of g, you will know what g prime of 2 is. Okay. Well, all I did to find the slope of f and the slope of g was just pick a couple of points off of that I thought were on these two lines and use the slope formula to calculate. So I got that the slope of f was -1. Okay, and so that's what f prime of 2 is. It's -1, and I got the slope of g was 2. So g prime of 2 is 2. Okay, just from picking off the slopes of these lines. And that, the only reason I can do that, of course, is because f and g are straight lines, right? So their rate of change or their derivatives is going to be their slopes. So I just filled in those slope values right for f prime of 2 and g prime of 2, and then did the arithmetic, and we came out with 1. So turns out to have a nice derivative there, p prime of 2, even though I don't even know what the graph of p looks like, and I don't even have a formula for the function p. I know that p prime of 2 is okay, now for problems 8 and 9, these are all just differentiation problems, right? So I'm not going to go through, these are too many to go through one by one. And so I've got all of the steps written down on the review. So you can look at the steps on the review sheet to see how to compute these derivatives. Okay, so I don't really have to go through these steps. You can read them off of the review sheet. However, remember, you can look at, you can go and visit Madison's review on Monday. Madison will have a review on Monday at, I think it was 9 a.m. Before the, it was either 9 a.m. or noon. So whatever Madison's SI session is on Mondays, you can find that on Blackboard. That information, I think also on WebAssign announcements, you can find that information. Then just go and ask if you have any specific questions on some of these derivative problems. Okay, you can also make an appointment with Math Center, right? Okay, an online appointment with the mass center if you have questions about these some of these derivative problems and the steps on those. All right, let's look now at problem number 10. And this is an applied problem. So we're given here a subatomic particle, and it just moves left or right on a straight line. Okay, so it's moving to the left or right, but it's moving on a straight line. So you can think of it, maybe it's easy to think of it as moving along the x-axis, okay, because the x-axis is a straight line, right? So think of, you've got a subatomic particle that's moving along the x-axis, but it can move to the left, or it can also move to the right on the x-axis from an initial position. And this function S will give you the particle's distance in meters from its starting position, okay, a certain number of elapsed seconds, okay, after it started moving, all right, or after we're observing it, okay. So S gives you the position of the particle, in meters after t elapsed second, right? Okay, so first things first is, what is the initial position of the particle? So just plug in 0 for t here, right? Because initial time would be time 0, and you get 2. So its initial position is 2. Okay, so that's easy. That's just an algebra problem. Second question is where calculus comes in. It wants to know what is the initial velocity of the particle, okay? And so velocity is going to be the derivative of the position function, right? So you need to find the derivative of the position function. That's easy to calculate, though. That's just 3t squared minus 3, and then evaluate that at 0, okay? Because initial would be at time 0. So you get minus 3. So our initial velocity is minus 3. Don't be confused, because that velocity is negative. That just means that the particle is moving in the negative direction, okay? Or in this case, to the left, right? So you can't have negative velocities. And then part C there is what's the acceleration of the particle after 1 second? Acceleration is derivative of velocity. All right, so here's the velocity function. So just take its derivative. That's the second derivative of the position function, and you get easily 6t, right? Evaluate that at 1 after 1 second, and you get 6. So its acceleration after 1 second is 6. And finally there, at what time is the particle first at rest? Not moving at all. At rest means not moving. Well, at rest means the velocity is 0, right? Okay, so we just set our velocity function to 0 and solve that equation. So you have minus 3t squared minus 3 is equal to 0. There's a quadratic equation to solve. You can solve it by factoring, and you end up here with these two values for t. We'll strike the negative one because it doesn't make sense to have negative elapsed time. So we have just t equals 1. So after 1 second, the particle is at rest. That probably means it's changing direction, but not necessarily, okay? So it's probably switching from moving from left to right, or right to left after 1 second. And at that brief instant after 1 second, since it's changing direction, it will be at rest. Okay, let's try now another applied problem here, okay? All right, so this one is just a little bit tricky because of the formula. So it says we have a lake, and it's stocked with fish, and there are 500 fish there initially, okay? And we want to know, we want to know several things, but this function gives us the population of the fish T elapsed months after we stock the pond. Okay, so it's initially stocked with 500 fish, and then after T elapsed months, we can use this formula to predict what the population of fish is going to be, right? If you take a look at the graph of this function, see what that graph looks like. So it looks something like this. So initially, it looks like the fish population is climbing, right, for a few months, right, up to, what does that look like? Maybe 7 months or something. The fish population is climbing, and then it begins a slow decline, right? Okay. So after 40 months, a little bit more than 3 years, it's fallen back down to, about 550. Still more than initially was there, but less than the peak population, which is going to occur after 7 months. All right, so the first thing we're asked for is just pretty simple there, right? What's the fish population after 10 months? So that's not a calculus question. We just have to plug 10 into our population formula, right? And do the arithmetic, and we end up with approximately, I rounded off a little bit here, we ended up with approximately 633. Okay, so after 10 months, we have about 633 fish in the pond. The more calculus question, of course, is this one. At what rate is the fish population changing after 10 months? So that is a derivative question, right? That's a rate of change question. So we're going to have to find the derivative of this function and then evaluate it at 10. So to find the derivative of this function, you want to use the quotient rule. To find the derivative of this function, you differentiate term by term. So you start with the derivative of 500, but that's a constant. So that's going to have derivative 0. And then the second term is the hard one, right? You need to use the quotient rule to find the derivative of 2000t over 50 plus t squared. So that's what I've shown happening here in this problem. This is the applying the quotient rule to find the derivative of that second term in the population formula, right? Remember, the quotient rule says you take the derivative of the top times the bottom minus the top times the derivative of the bottom, and then divided by the bottom squared. So that's all this is just the quotient rule. And then I've simplified that sum. And when you simplify that, you end up with ultimately 100,000 minus 2,000 t squared over 50 plus t squared squared. Okay. So there is the rate of change of the population. And we want to evaluate that at 10. So I just plug 10 into this formula, and we end up with about minus 4, which sort of corresponds to the graph, right? After 10 months, right there, the fish population is declining, right? Okay, you can see the curve there has negative slope. And in fact, it's declining at that time at a rate of 4.4 fish per. Okay, that's the rate of change after 10 months. The last question is kind of a conceptual question. We're going to talk about how we can, a little bit later, about how to answer this question exactly. But here it's just an intuitive question. It says, using the graph, when do you think the fish population is decreasing most rapidly? Okay, my guess was at t equals 15. You may have come up with slightly different answers. The reason I gave that guess is that that's where the curve appears to have the steepest negative tangent line, right? Decreasing would have to have the tangent line with the steepest negative slope. So, of course, where the population is decreasing, you're going to have tangent lines with negative slopes. So you're going to have tangent lines going downhill from left to right. And I thought right after 15, right there, was when the tangent line would be the steepest. Okay, so when we would have the steepest negative slope, right? That was just my visually eyeballing it. Over here, I think the rate of decrease is a little bit less, right? Because the curve is flattening out. Up here also, I thought the curve was a little bit less steep because it was flattening out close to this turning point. But right there at 15, I felt like that's where the curve was steepest in the negative direction, right? Okay, right there. Okay, finally, just one last problem now. So this is really a fairly simple problem, but it can be confusing when you see it for the first time. So cubic polynomials are polynomials that have a third degree. That means that the x is raised to the third power. So a quadratic polynomial, a second degree polynomial, would have an x squared term in it. You're very familiar with quadratic polynomials, but cubic polynomials have x cubed terms in them. So here in general is what a cubic polynomial will look like. Okay, it's going to have an x cubed term and an x squared term and an x to the first power term and then a constant term. And these values, a sub 3, a sub 2, a sub 1, a sub 0, those will change from cubic polynomial to cubic polynomial. So you get different cubic polynomials by changing the values of these coefficients, a sub 3, a sub 2, a sub 1, and a sub 0. Okay, but in general, all cubic polynomials have this form. They just differ by different choices of these coefficients. All right, well, let's find in general what the derivative for a cubic polynomial looks like. So we're going to differentiate this formula without choosing specific values for a3, a2, a1, and a0. Okay, so remember, these are not variables now. These are constants, and the variable here is x. So when you differentiate this formula, well, you just differentiate term by term, and you can use the power rule on every term. So for differentiate this first term, just bring the 3 down. So you get 3 times a sub 3 times x squared, right? Subtract 1 from the exponent. For the second term, bring the 2 down. So you get 2 times a sub 2 times x. And then for the third term, since this is just a constant times x, you're going to get just a1. And since a sub 0 is a constant, its derivative is 0. So in the derivative, the a sub 0 does not appear. So here's what for any cubic polynomial, here's what its derivative in general is going to look like. 3 times a sub 3 times x squared plus 2 times a sub 2 times x plus a sub. And what we want you to do with that general derivative is show that any cubic polynomial has at most, maybe it has none, but it has at most 2 points where the tangent line is horizontal. Well, how do you find on functions where they have horizontal tangent lines? You take the derivative, right, and you set it to 0. So if you take a cubic polynomial, its derivative always looks like this, has this form, just different choices for a3, a2, and a1. Set that to 0 and solve that equation, and that will give you where on the cubic polynomial the tangent lines are horizontal. Well, of course, that's going to have this equation is going to have different solutions depending on our choice for a3, a2, and a1. But no matter what choice you have for a3, a2, and a1, you still can have at most 2 solutions to this equation. You can have only 2 solutions to this equation because this is a quadratic equation. It has x squared in it, right? And remember, when you solve quadratic equations, you can have at most 2 solutions. Quadratic equations can only have 2 solutions. So what that tells us is, oh, if quadratic equations can only have 2 solutions, that means cubic polynomials can only have 2 places where the tangent line is horizontal. Oh, that's interesting. So that tells me that cubic polynomials can only have 2 turning points, right? They can only have 2 turning points, right? You can't have more than 2 places where the curve switches from increasing to decreasing, or vice versa. So that means that cubic polynomials, their graphs cannot be that complicated because their graphs can only have 2 turning points on them. They can't have lots of wiggles in them, right? The graphs of cubic polynomials cannot have lots of wiggles in them because they can have at most 2 turning points, right? So if you had lots of wiggles in your graph, it would have had lots of turning points, but that's not possible for cubic polynomials. Okay, so there's our discussion of some of the problems from the sample test, and I'm sure you'll see problems like these on the test as well. So remember to go back through the derivative problems. I mean, the differentiation problems, that was problems 8 and 9, right? And look at the solution sheet, right? Okay, for the steps of computing those first and second derivatives. Okay, so good luck on the test.